Hello everybody, this is Dr. Christopher White, and in today's presentation we're going to continue with the Precambrian Earth and its life history. So this is the Proterozoic Eon. Let's get going. So the Proterozoic Eon is the real monster of the geologic timescale. So it covers a period between 2.5 billion years ago and 542 million years ago. So it's about 2 billion years in size. Now, like the Hadean and the Archean, most Proterozoic rocks contain no macrofossils. So this is obviously a bit annoying for a geologist because, as we know by now, geologists love macrofossils. They help us to divide up the rock record and they allow us to correlate units of rock over large distances. So unfortunately, not having macrofossils does hinder our ability to divide up the Proterozoic somewhat. However, although a substantial portion of the exposed Proterozoic rocks that we have undergone some degree of metamorphism and deformation, there are some areas of Proterozoic rocks that are in a near pristine condition. So this obviously differs substantially from Archean rocks. So if you remember, most Archean rocks are either greenstone belts or granite gneiss complexes. Now, both of these types of rocks are metamorphic terrains, and in most cases they've been quite strongly metamorphosed, so this means the original rock has been completely lost. In the case of the Proterozoic, on the other hand, yes, there are some areas of Proterozoic rock that have undergone very extensive metamorphism and deformation. However, there are also some areas where the rocks are in, near original condition. And obviously this is extremely helpful for geologists because being able to, get at the rock that's about as good as you could possibly hope really helps us to understand what was going on in certain areas during the Proterozoic. So just to give you some idea, here is a picture of the Grand Canyon. So if we look at this image, what can we see? Well, this red line here marks the transition between the Precambrian and the Cambrian. So the units below this line are obviously going to be Precambrian in age, and the units above it are going to be Cambrian. And so what we can see here is we have a sequence of rocks which are referred to as the Unkar group. And essentially it's a sequence of sandstones, mudstones and carbonates. So these are passive continental marine sediments. And so what we have is a sequence of relatively pristine rocks that we can go to and we can analyze, and it helps us to get an understanding of what was happening in the Grand Canyon area during the Proterozoic. So on the whole, these rocks are in great condition. You can see there is an ever so slight tilt to them, so they have been ever so lightly deformed, but on the whole, in terms of metamorphism, they are relatively unmetamorphosed. So the change from the Archean to the Proterozoic is arbitrary. So we've already discussed how essentially the boundary is set at 2.5 billion years because it's a nice round number. However, its location is based on a few observations, so we can see some changes as we transition from the Archean to the Proterozoic. Now, the first and most obvious change is we begin to see the appearance of more aerobic sediments. So these are sediments that contain oxide minerals, particularly iron oxide minerals. Now, this is obviously telling us that the atmosphere is getting more oxygen rich. So the more oxygen your atmosphere has, the more likely it is to form oxide minerals on the surface of the Earth. Obviously, if there's very little oxygen, the chances of you forming oxide minerals are quite low. So the fact that we see this shift and we see the appearance of oxide minerals in greater quantities in Proterozoic sedimentary rocks is a strong indicator to show us that the amount of oxygen in the atmosphere is on the increase. Now, we also begin to see the appearance of facies associated with passive continental margins. So if you remember, a passive continental margin is like the east coast of North America. Essentially, it's a continental margin where nothing particularly spectacular happens. Don't have a mountain range, don't have volcanoes, don't have earthquakes, don't have tsunamis. In terms of life, it's a pretty dull place to live, and life loves dull, safe environments. So If you also remember, going back to the Archean, the vast majority of continental margins actually were active. So they were active subduction zones, which means mountain ranges, volcanoes, earthquakes, tsunamis, which are not great environments for life to exist. So what we see as we go into the Proterozoic, we start seeing more of these passive continental margins. These are peaceful, safe environments, and life begins to take advantage of those nice, safe environments. We also begin to see the appearance of epicontinental marine deposits. So these are shallow bodies of water that form on the continental crust, typically when there are high sea levels. So the sea level goes up, the ocean moves onto the land, and it will tend to create these smaller, shallow seas. Now, what this obviously means is we have the first evidence of marine transgressions and regressions. And the only reason we can see this is because we have these near pristine Proterozoic rocks that can show us that this process is taking place. We also see a reduction in the rate of granite gneiss complex and greenstone belt formation. Now this ties back to the passive continental margin observation, and it shows that during the Proterozoic the amount of subduction and the rate of subduction was decreasing. So we also see a change from the highly metamorphosed granite gneiss complexes and greenstone belts to less metamorphosed or to unmetamorphosed rocks. As we've described, we do have some Proterozoic rocks which are in pretty good condition. The final thing we see is an unconformity, and this particular unconformity is approximately along the Archean to Proterozoic boundary. So this would suggest, as we transitioned from the Archean to the Proterozoic, in the case of North America, most of the continent was exposed. It was open to erosion, and this obviously means lost rock, and of course lost rock in geology means lost time. And so what we can see is, as we transition from the Archean to the Proterozoic, we have a situation where North America is exposed, it's undergoing erosion, and then as we transition into the Proterozoic, we then get the deposition of sediments across this erosional surface, producing an unconformity. Now, it's actually a little bit difficult to say whether this unconformity represents the boundary between the Archean and the Proterozoic. It could actually be that maybe the unconformity is down here, so it's part of the Archean, or maybe the unconformity actually represents a period of time up here, so maybe it's Proterozoic. But we know this boundary falls somewhere around the Archean Proterozoic boundary. And so in North America especially, if we go around, we can find this particularly large unconformity. Now, if we look at the Proterozoic itself, we can see that it's split into three main eras. We have the Paleoproterozoic, the Mesoproterozoic, and the Neoproterozoic. So the Paleoproterozoic are the oldest rocks, and the Neoproterozoic are the newest rocks. And now try and remember that, because the terms Paleo, Meso, and Neoproterozoic are going to be coming up quite a lot during this presentation. So here is the aforementioned unconformity. So here we have the very heavily metamorphosed rocks of the Vishnu schist. So these are Archean rocks. And on top of them, we have Proterozoic sedimentary rocks of the Unkar group. And we can see the beautiful sedimentary layering there. We can pick out individual beds of rock. We can see the textures. And if you go up and look at it, you can see that it's actually a sedimentary rock in pretty decent condition considering its age. Now, this is the unconformity itself coming through here. So you can see it's an angular unconformity. We have horizontally bedded rocks above and vertically bedded rocks below. And obviously, this represents a period of erosion. So we know that as we transition from the Archean to the Proterozoic, North America is exposed to the atmosphere and it's undergoing active erosion. Now, as we've also discussed, whether this boundary actually represents the exact Proterozoic Archean boundary is up in the air. It could, this unconformity could represent a period of time just inside the Archean, or it could represent a period of time in the Proterozoic, but it approximately falls along the Archean Proterozoic boundary. Now, when it comes to trying to find features like this that allow us to split up the Proterozoic, because we have some areas of rocks which are in good condition, we can actually start to find features that would allow us to separate the Proterozoic into different subunits. Now, an attempt in 2012 was actually made to split up the Precambrian based on some of these observations that we can make, and so it allowed us to split up the Proterozoic into slightly smaller units, and it set the Archean Proterozoic boundary to 2,420 million years ago, so 2.4 billion years ago. And this boundary was based on the first appearance of glacial sediments, which is quite a good thing. The glacial sediments are quite easy to identify, and they are reasonably widespread in Proterozoic sequences. The problem is, with a lot of these observations that we can make of Proterozoic rocks, what we're looking at tends to be a localized feature. So this unconformity that we can see here, which is, approximately falls on the Proterozoic Archean boundary, is great if you're in North America. Doesn't really work in other places. Same with the glacial sediments. I do apologize for that. Same with the glacial sediments. So in some cases, the glacial sediments are wonderfully exposed, and you can use them to see where the Proterozoic Archean boundary falls. However, in other parts of the world, there are no glacial sediments visible, so you can't see where the Archean Proterozoic boundary falls. So we have attempted as best we can to actually come up with, anchored boundaries for the Precambrians. That's the Archean and the Proterozoic, but they haven't been accepted yet, and the boundary observations that we do have, the things that we're using to define the boundaries, are often not universal. So it's not a perfect situation, but when it comes down to it, it's the best we can do. So the Proterozoic is marked by a period of substantial atmospheric change. So during the Proterozoic, we start to see photosynthetic bacteria, so algae, increase in abundance, and we begin to see the atmosphere become more oxygen rich. Now this leads to the formation of a particular type of rock, which is called a banded iron formation. And banded iron formations are important for a couple of reasons. Number one, they show us how the atmosphere was changing in the Proterozoic, but arguably the more important reason that we are interested in them is because they are the world's primary source of iron ore. So the Proterozoic marks the first appearance of oxygen-dependent organisms. So this obviously shows us that, by the time we're into the Proterozoic, we have an atmosphere that's beginning to become more oxygen rich, and because it's becoming more oxygen rich, we begin to see the appearance of organisms which will actually use oxygen to respire. We also see the development of cells that have cell nuclei. So if you remember, cells come in two types. There's the prokaryotic cells, and those are cells like bacteria, where the genetic information, DNA, is just floating around loosely inside the cell. The other type of cell that we have are eukaryotic cells, and in eukaryotic cells the DNA is actually put into a confined space that has its own membrane that we call the nucleus. So it's bundled up tightly and neatly and put into a corner of the cell so it doesn't get in the way of other things. And so what we begin to see is we see the appearance of these eukaryotic cells during the Proterozoic. So the development of a nucleus is helpful because it actually gives additional room inside the cell. And this means because there's more room inside the cell, it means there's room for things that we call organelles. So these are things like the endoplasmic reticulum, mitochondria, chloroplasts, essentially organs in the cell, parts of the cell that allow the cell to function more efficiently. And because all of a sudden we have room for these organelles now and they begin to appear, what we see is this shift from slightly less efficient prokaryotic cells to slightly more efficient eukaryotic cells. And as we've discussed, when we look at Proterozoic rocks, we also see the appearance of the first known glacial events. So we can begin to see glacial sediments and the effects that those glacial sediments had on the rocks around them. So let's look at Laurentia. So the continent of Laurentia comprises a substantial portion of the central, northern and eastern United States and Canada, along with Greenland, a portion of Scotland, and possibly even a bit of northern Europe. So we have several land masses which formed during the Archean. So these are pieces of continental crust. And what we're going to see is those pieces of continental crust are going to collide in the early Proterozoic, and they're going to form the core of the continent which we call Laurentia, now modern day North America. So mass was added to this core through sediment deposition along the margins of Laurentia, and repeated collisions and accretions of island arcs along Laurentia's eastern and southern boundaries. So what we're going to see is Laurentia is going to form in the early Proterozoic, and we're going to steadily see Laurentia getting larger as we go through the Proterozoic as more and more material gets added to Laurentia's margins. So here's our situation. So this is about 2.5 billion years ago. So the grey areas that we can see here are areas of Archean continental crust. Okay, so one of these areas you might be familiar with already, this is the Superior Province. So that's a term that's come up before, but most of these other blocks you will be unfamiliar with. So what's going to happen is in between these pieces of continental crust, obviously we have areas of oceanic crust. So obviously we've got to subduct this oceanic crust, and in the process of subducting the oceanic crust, the pieces of continental crust are going to move towards each other, and obviously they will eventually collide and suture together. So the process of suturing is essentially two pieces of crust locking into each other and becoming attached to one another. So between 2.5 and 1.8 billion years ago, the Archean landmasses collided and sutured together to form the core of the Laurentian continent. So the collisions resulted in several orogenies. If you remember, an orogeny means mountain building event, with widespread metamorphism, deformation and intrusions. So key examples of these orogenies are the Thelian orogeny, that's between 1.92 and 1.96 billion years ago, and that's when we have the slave and the ray cratons collide. So if we just go back, we can see there's the slave province and there's the ray province, and those two will collide about 1.92 to 1.96 billion years ago, and we'll obviously get a mountain range produced by that collision. We also have the Trans-Hudson orogeny between 1.82 and 1.84 billion years ago, and that's when we get the Superior, the Hearn and the Wyoming province colliding. So, when they're wrong way there, sorry, there's the Superior, there's the Hearn, and here's Wyoming. So we're going to see Wyoming is going to move approximately northeastwards, Superior province is going to move approximately westwards, and the Hearn province is going to move approximately southeastwards, and the three of them are going to collide with each other and suture together. And we also have the Pinocchian orogeny. So that's about 1.85 billion years ago, and in the case of the Pinocchian orogeny, it's actually produced by several island arcs hitting the southern margin of the Superior province. So it's going to happen round about there. Now, also I should point out that these yellow areas here represent regions where we start to see passive continental margin sediments being deposited. So these are areas along the edges of these continents where we do not have subduction. So these are relatively passive regions where the coastline is relatively stable and boring, and as discussed, life likes these kinds of environments. So by 1.8 billion years ago, what's happened? Okay, so obviously here's our Trans-Hudson orogeny, produced by the Superior province, the Hearn province and the Wyoming province coming together. So this pink area here would have been an area of high ground. It would have been a mountain range. Obviously, we also had the Thelian orogeny here between, between the Ray province and the Slave province. So we're going to have an area of high ground running along here as well. And here's the Pinocchian province down here. So this is produced by the impact of several island arcs along the southern boundary of the Superior province. So we got raised terrain here, here, and here. Now, the other thing you'll notice is we now have all these orange areas. So the orange areas come in two forms. We have the lighter orange areas, which are defined as juvenile arcs. So if you remember, an arc means a volcanic band, essentially. So these can obviously be in the form of island arcs, or they can be in the form of continental arcs, so volcanoes within mountain ranges. In both cases, they're associated with subduction. Now, we also have what are referred to as juvenile origins. So these are areas of the crust that have been deformed and essentially compressed, and that's produced elevated terrain, so hills and mountain ranges, and that's once again due to compressive tectonics associated with convergent plate boundaries. Now, these juvenile origins, on the other hand, they are not the island arcs themselves. They represent the material that was in between the island arcs, so bits of oceanic crust and the sediments that were part of the seafloor in between the island arcs. So that's what we're seeing in those environments. So what we can see, by the time we're 1.8 billion years ago, we can see we have the core of Laurentia right here. And you can see that we have the addition of island arc terrains along the edge of Laurentia, and that's going to start to make the continent bigger and bigger. So this is the time when we need to really start discussing things called Wilson cycles. So Wilson cycles are named after Tuzo Wilson. He's come up before. So he was the scientist that realized that transform plate boundaries must exist. So Tuzo Wilson came up with the idea of Wilson cycles to describe the sequence of events that occur when a new ocean basin forms. So an ocean basin is going to form through the process of rifting. Now, what Tuzo Wilson realized is that yes, an ocean basin is going to form through the process of rifting, so an ocean basin is going to open up, but obviously eventually the ocean basin is going to have to close and be destroyed. So a Wilson cycle essentially goes through the entire process from the formation of your ocean basin through rifting all the way through to its eventual destruction by subduction, which will obviously then lead to a continental collision and the formation of a mountain range. Now, Wilson cycles can be relatively short, so a good example of a Wilson cycle that's going to be relatively short will be the East African Rift Valley or the Red Sea. So at the moment, I'm sure you remember, the area of approximately, the area represented approximately by Somalia is trying to pull itself off the eastern side of Africa. So this is resulting in the crust becoming extended, so it's being stretched, and that's resulted in the formation of the East African Rift Valley. Now, if there was enough time, Somalia would eventually rift all the way off Africa, so Somalia would then start moving eastwards into the Indian Ocean, and obviously this would mean a new sea would open up between Somalia and Africa. This would be a new bit of oceanic crust. However, this isn't going to happen, because before this can happen, Africa is going to fully smash into Europe, and this is going to essentially cause the extensional tectonics in this region to more than likely stop. So this would be a failed Wilson cycle, never made it all the way. On the other hand, there are some Wilson cycles that are very, very long, and a good example of a very mature Wilson cycle is the Atlantic Ocean basin. So we know the Atlantic Ocean started forming 250 million years ago, so during the very early Triassic. And since then, the Atlantic Ocean's been getting larger and larger and larger and larger. And it's probably going to keep getting larger for somewhere in the region of the next 20 to 50 million years. And then eventually a subduction zone will open up on one or both sides of the Atlantic, and the Atlantic seafloor will be destroyed, and this will allow Europe and Africa and North America and South America to move towards each other again, eventually resulting in a collision and the formation of a very, very large mountain range. So the diagram in front of us covers the basic stages of a Wilson cycle. So a Wilson cycle begins when we have adjoining convection cells, and these are going to be located under a piece of continental lithosphere. So if you remember, the Earth's mantle is constantly convecting, so mantle rocks get heated up, that makes them naturally buoyant, they want to rise. As they rise, they cool down, becoming denser again, and then they sink. So we have this convection where we have hot material constantly coming up and cold material being brought back down to be heated back up again. Now, as far as we can see, a lot of these situations of rifting are associated with areas where we have mantle convection cells coming up and going one way, and right next to it we have a mantle convection cell coming up and going the other way. And so what this means is the natural movement of the mantle rocks, in this case to the left and in this case to the right, is going to start pulling on the continental lithosphere. So it's going to start to try and make this piece of lithosphere go off to the right, and this one's going to try and make this piece of lithosphere go off to the left. And this means this area of continental lithosphere in the middle here is going to become stretched, it's going to be extended. Now, at the same time, the interfaces between these convection cells are a preferred conduit along which mantle plumes will rise. So a mantle plume, if you remember, is a big ball of magma that comes flying up from the core mantle boundary and then gets stuck underneath the lithosphere. So in this case, because we have the interface between these two cells, the mantle plume is going to come shooting up and it's going to get stuck here beneath our rift area. Now, the thing the mantle plume is going to do is it's also going to help to stretch the crust. So think about it, the mantle plume naturally wants to rise because it's buoyant and it's going to start to make the crust want to dome up. Okay? Now, if you remember when you were a kid and you had a flexible ruler, you started to bend the ruler and you would bend it and you would bend it and you would bend it, and maybe if you're unlucky you bent it too far and the ruler would snap. Well, the same thing is going to happen to the continental crust. We're going to start doming it, so it's going to start flexing. It's going to flex more, it's going to get pushed up more, and then eventually, if you push it too far, it's going to fail. So, a combination of these convection cells and mantle plume activity is going to put this region of our piece of continental crust into extension. It's going to be stretched, and that's going to cause the crust to fail, leading to the formation of a rift valley. So because the crust fails, we get lots and lots of these very, very steep normal faults forming, and so bits of rock are dropping down one after another, and it helps to create this stepped appearance, which is pretty diagnostic of a rift valley. So okay, so stage one is the formation of our rift valley. Now what's going to happen is because the crust starts getting thinner, the mantle rocks right here underneath our rift valley, well, all of a sudden the pressure on them is going to start decreasing. So remember, these are going to be very, very hot rocks, which are normally under very high pressure, so they can't melt. However, when we start to drop that pressure, well then all of a sudden the mantle rocks can begin to melt through the process of decompressional melting. Now this is going to lead to the formation of mafic magma. So the mantle rocks are going to melt and it's going to form mafic magma. Now, this mafic magma is obviously going to want to make its way through the crust, so it's going to start pushing its way through the crust. As the mafic magma pushes its way up, it obviously has to make space for itself. So in order to make space for itself, it has to push this piece of crust off to the left and this piece of crust off to the right. And so what's happening is the passage of this mafic magma through the crust is helping to drive this piece of crust that way, this piece of crust this way, and in the process the mafic magma crystallizing is going to end up forming oceanic crust. So over time we're going to get enough of this mafic material building up to the point where we have a fully functioning oceanic divergent plate boundary. So at this divergent plate boundary we're going to have mafic magmas produced through the melting of the mantle rocks underneath. The magma produced is going to rise up through the crust, where it's going to crystallize and solidify as solid new oceanic crust. Now obviously every time magma moves towards the surface it pushes the crust apart a little bit, and that helps to move these pieces of continental crust further and further away from each other. So over time the formation of this new oceanic crust is going to push our two pieces of continental crust away from each other, just like the Atlantic Ocean is doing now. So the Mid-Atlantic Ridge in the North Atlantic is pushing North America off to the west, pushing Europe off to the east, and so it's increasing the distance between the two continents. Now eventually a subduction zone will open up on one or both sides of our ocean basin. So we'll get a subduction zone in this case forming here. Now this is going to cause the oceanic crust that we formed here to subduct underneath the continental crust that we have here. And it's obviously going to result in the formation of an active continental margin. So we're going to have a mountain range, we're going to have volcanoes, we're going to have earthquakes. Now, as the oceanic crust is subducted down into the mantle, it obviously means the distance between our piece of continental crust here and our piece of continental crust here gets smaller. So they're starting to move back towards each other again. Obviously this process will continue, and eventually the two pieces of crust will collide with each other. That will obviously produce substantial deformation, so it will lead to the formation of an orogeny, so a mountain range, and we'll end up with a lot of topography, so we'll get lots and lots of high ground formed by this event. Obviously over time, once the collision stops, everything will calm down, the mountain range will be eroded away, and you'll be back to a pretty boring flat piece of continental crust, which will then eventually rift again, and so the cycle will continue. And so this is the basic principle of a Wilson cycle, and we can see these have been happening throughout geologic time. So it's a model that works based on the evidence that we have. Okay, so this is a good place to stop part 1. So get up, have a walk around, go and get a glass of water, sit down for 5 to 10 minutes and relax, and then please come back for part 2.